So here I am at the end of the day. We have 40 minutes after which alcohol will be served. I have 132 slides. So, for those people, a few people in the audience who saw a talk with the same name and this same title slide in the States a few months ago, this is not the same talk. One of the things I like to do is say exactly the opposite of what I said before. So this is all the things I said about evidence in the States, but I'm going to make exactly the opposite arguments, and I'm guaranteed to be right part of the time. So I want to talk about evident code, and I want to talk about it in the context of projects that I work on. And the idea behind evident is that the code is perceptible, that it's obvious what the code does, that it's apparent. This is a desirable property, and I think that probably we're here because we think Clojure takes us in the right direction for that. I certainly feel that way. And so I'm going to look at this from the context of Clojure itself, and also from Datomic, which is what I've been working on for the past couple of years. So one thing that people will argue in favor of when they're worried about code being evident is this idea of declarative programming. And so the idea, and I have a lot of these definitions, but you can just read the red part, or maybe not. I don't know, at the back of the room you may not be able to read the red part either. The idea behind declarative programming is you specify what instead of how. So here are a couple of declarative approaches to rock, paper, scissors. In the top left, we have rock, paper, scissors expressed as a map. And on the bottom right, we have rock, paper, scissors expressed as a set of vectors. These are both data representations. If I was fancy and had a blog with good colors on it, I could call this a DSL for rock, paper, scissors. Is one of these representations better than the other? I'm not going to answer that question. I'm just going to leave it hanging. I'll let you think about whether one of these representations is better than the other. However, I am going to expand the game to rock, paper, scissors, lizard, Spock. And I'll let you go back and think about the representations there. Having that declarative representation in hand, I may still have to write a program. So here is a short Clojure program, which is functional, which will tell me, given two players, rock versus scissors, who wins. But this functional approach really is not as general as it could be, because this notion of a function, this is a function of two inputs, one player and another, and what's the output? Who won? If I thought of this in terms of logic, I could think of it as a relationship between two players and who won. And the big advantage of that is that I'm no longer obliged to provide these two pieces of input in order to get output. And I know people have seen talks about logic programming, so I won't beat this to death. But if I were using data log, I could have a pattern like that said winner, loser. And notice that in the pattern itself, I haven't said anything about which one of these variables, if any, I'm going to bind. So if I happen to bind nothing, that data log pattern says, tell me all of the combinations. Right? Tell me everything about the game. If I bind winner to Spock, it's going to say find everyone that Spock beats. But I can also bind more than one thing, right? Bindings can happen more than once in a logic program, so I could bind it to a collection of things and say, give me all the people that Spock or Lizard beat. Or I could have a pattern, more than one pattern, and then have the same variable appear in multiple patterns, which now starts chasing relationships. Right? So now I know that the winner beats somebody in the middle who beats up on the loser. And the idea here, and the thing that I want to point out, is that being declarative by itself is insufficient. I can be completely declarative and then turn around and write an imperative loop over my declarative data. Right? I can sit down and open up any language that I want, make a data structure, and then write a completely imperative program that interprets that data structure. And that may be appropriate in some cases, but where possible, it's nice to go functional rather than imperative. And it's nice to go logical rather than functional. And structure matters. If you go back and try to code these against those two different data structures that I gave, you'll find that they have different characteristics. And there are other data structures you might have chosen as well. This should be really easy. How many people are against abstraction? I'm glad to see at least one hand go up. How many people don't raise your hand no matter what anybody ever says? Oh, more hands for that. So I love this dictionary definition. Abstractions are formed by reducing information. The job of abstraction is to reduce information. Now, let's put that up against Clojure's model for time. Some of you have probably seen this slide that Rich uses to talk about the time model. So that dotted line box is around one of Clojure's reference types, and it is transitioning from value 1 to value 2 to value 3 to value 4 over time. Those transitions are functional, right? So up here above the box, you see the functions that are transforming the value from, if this is ink, it's 1, 2, 3, 4. Those are the transformations. And then down at the bottom, there are perceivers. And Clojure has a great advantage in dealing with this over most languages in that it's mostly functional, and then it has this perception model, and these guys can perceive to their heart's content, right? They don't need to have any coordination with anything else that's going on in the system, and you'll hear Rich talk more about this, I expect. Now let's pit that against abstraction. If I have an abstraction around action, where I'm asking the system to do something, then that abstraction is basically saying, you don't have to know all the details about this action, right? You don't have to know everything. I've abstracted. I've reduced the information content required to initiate an action. That could be a good thing, right, if used wisely. On the flip side, if I have an abstraction on the perception side, right, I have a perfectly good value, but I don't give you that. Instead, I abstract. What am I doing at that point? I'm just stealing from you. Right? And this is a very difficult thing to explain to people who are coming from an object-oriented background. Because abstracting down here is what they do every time they make a Java bean with getters and setters on it. Okay. Now, the other thing that I would point out there is not only are they not helping themselves when they do that, but they're actually misusing the tool of abstraction. Right? So if I have a person object that has a first name and a last name and a middle name, and then I have an interface with first name and last name and middle name, have I actually reduced the information? No, I'm just passing it through. I'm just passing that information through. So, I don't know, this picture has helped me think through explaining that piece of it to people that are still trying to come from the OO background, and they've been told for so many years to encapsulate. Don't encapsulate information. Information is a value. You should give it out. If you don't have it in the right shape, then transform its shape and give that out. So that's one problem that we have with abstraction. Another thing that we get wrong with abstraction is abstractions are often way too big. So this is the map interface in Java. And the Java Collection API is a pretty good API, right? We've gotten a long way with it. But there are some issues here. The obvious functional programmer criticism of this API is that it combines perception and action, right? So there are getters and setters. And so, for example, the Clojure data structures, when they implement these interfaces, just throw an exception on all the things that shouldn't have been there in the first place, right? All the things that try to set things. But there's another problem here, and it's a problem that became more apparent for me while working on Datomic, and that is that this is not really a good interface to represent, say, an entity. And the reason is, again, that it's way too big, and in particular, it has equals and hash code, and those have rigorous definitions. And if you're going to be a map, if you're going to implement this interface in the Java ecosystem, you have to be ready to play the equals and hash code game as defined in the interface, which is not a very fun game to play if you have a richer data structure, right? If you have an entity that actually represents the ability to navigate down or up in the database, which Datomic entities do. Because that guy's not really, he's more than a map and less than this interface at the same time. So this interface is way too big. And this interface is a lot closer to nailing it for a particular purpose. I'm not saying this is the only interface you need to pull out of map. Right? There are a half dozen other interfaces hiding in their cache and other things. This is the one that Datomic uses to represent entities. And in particular, this represents that it's impossible for entities to be maps because they cannot conform to the hash code and equals requirements, which are over the top. Now, that interface is too big. That one is just right for the job. But the reality is the appropriate number of methods in an interface is 0. Stop making abstractions. Resist making abstractions. Abstractions are relatively few and far between. Make them carefully. But we have this incredible over-urge. It's an OO hangover to make abstractions where they are not. And then it actually poisons us and we can't see them where they are because we use the tool for abstraction all over the place instead of in the few places where it's important. Another thing that we do with our tool for abstraction is pour concrete on action. So this is a web servicey interface, and it's got things like set table name and get limit and blah, blah, blah. This is, I grabbed this from some web interface. And again, it's adding, I mean, these interfaces, these entry points are not really buying us anything. There's not an abstraction here. Right? What is the abstraction? The abstraction is communication. Here's a more generic version of the same thing. So this is the Transact API, again, borrowed from Datomic. And it's only got 2 methods. The other thing that's important about this, though, is that with this approach, once we said that the action is just I'm sending a request somewhere that's going to do something, and everything is actually happening in the data, what happens when you want to decouple your system and say, you know what, I need to go from synchronous to asynchronous with this? What happens when you have those big interfaces that are hiding you from the work you're trying to do? You can't even do it, right? You've built this knotted, combined thing step by step through your system, and you can't change how those steps work. You can't remote them. You can't easily say, I'm going to take this step and move it over here. But because this interface, it's not just that it has a small number of methods. That's part of it. But even if it had a large number of methods, the important thing is that it's conveying values. And so when we need to break this apart, if we say, you know what, we were wrong, Transact can't happen here, it's got to happen over here, it's not a problem. Right? It's a tiny API that's just moving data. So that's the total number of database update methods. In general, we were helped in writing Datomic by Clojure's protocols in a huge, huge way. I think people in the community understand these well. There have been a lot of good tutorials and explanations of the benefit here. Elevator summary, polymorphism doesn't live in your nouns. Right? Polymorphism lives in a separate place. And that has given us huge leverage, and it gives us the ability to change our mind after we've put code out there. Right? We have data out there. We want to add new abstractions to it. Our hands are not tied. A couple of examples of this. Storage is an abstraction in Datomic. Because of that abstraction, you know, when we launched, we said we were going to be Amazon Web Services only. And we got some community reaction that, hey, this is kind of cool, but it would be nice if it stored things somewhere else. The Postgres integration, so that it could use Postgres as a backend, took 1 day. Right? That's the whole job. And that is architectural agility. And it comes from abstraction. It does not come from test-driven development. It does not come from stand-up meetings. Right? It comes from having separation in your system that lets you change in big ways. I'm not saying those other things are bad. Right? I write tests, I go to stand-up meetings. I sometimes sit down because they get really long. I don't really know how to run them very well. On the perception side, there aren't very many abstractions around perception. And they really are generic abstractions. They're things like map and list and set. They're not things like person and bank account. But there are a few new ones in Datomic, in particular database and entity. So a couple of rules for abstraction. Make them fine-grained. Try to break them apart. If you have an interface with 10 methods in it, it's probably wrong. There's probably some useful subset hiding in there. I think the average size of a protocol in Clojure and Datomic both is probably 2.1. And I just make numbers up on the spot, so somebody go run a query and tell me what the actual number is. But it's tiny. And the largest one I know in Datomic is 7. So now let's talk about data. Data is immutable. We all know that. We're at a Clojure conference. But let's take a look at this quote. This is a quote from an article. I was I was in Copenhagen doing a talk about object relational mapping and the impedance mismatch. And while I was researching for that talk, I ran into this quote. And this is someone telling somebody how to fix their query. And the idea is I've got this query, I'm going over to the persistence layer, I'm going to get some stuff. And then I'm going to put hints on my query so that I can get the related stuff that I need. And there are two reasons that you might want to do that. One of them is what people call the n+1 problem. Right? I'm going to put this hint on my query so that when I go over there to some persistent store and bring something back, I know I'm going to need these other things. I don't want to have to make extra round trips. But the more fundamental reason that this happens is that if I go over there and then go over there a minute later, the world may have moved without me. Right? And so this is actually, although it doesn't look like it at all, this is actually a consequence of not programming with immutable data. Right? If your data from the data tier was presented to you as immutable data, you wouldn't have to worry about going back to it. Right? You could go back to it whenever you wanted, and this is a real terrible, I'll go ahead and say it, complecting factor. Those who are playing the drinking game, take one shot. Right? We just got something complected. Right? But this is terrible, right? Because you're trying to ask a question, but now you're trying to like freight train this huge thing because you don't actually have values to program with. Here's another statement. This one I'll summarize for you. It basically says active record sucks because it encourages decomposition. Isn't decomposition a good thing? Well, why is decomposition a bad thing? This is really just beating a dead horse, right? This is the same point, just with a different set of text. Right? I can't decompose because I'm not programming with values. And the point that I want to make here is that a lot of times we've talked about the benefits of programming with values, and I'm not going to even do that today. I just wanted to point out the things you're not worrying about anymore. This stuff is gone from your world when you program with values. Data is programmable. Right? I can manipulate it. My programs are made of data when I'm in a Lisp. Right? So I can program my programs. Is it an important characteristic that I need to be able to program my programs? How many of you have met little Robert Drop Tables? Right? His last name is semicolon drop table students, semicolon hyphen hyphen. Right? If you have a programming language that's not built out of data, and then other people need to write programs that write programs, it is not a pretty deal, right? Does anybody think that SQL injection is an issue of modest importance for us as an industry? This is a consequence of getting it wrong, right? It's a programming language that's not built out of data. Java is actually more programmable than SQL because Java, even though it does not have an information model for the Java source programs, there actually is an information model for compiled Java programs, right? There's a class file specification. I still remember how excited I was when I was advanced enough in my career to go into the deep voodoo world of reading the JVM spec book and learning how you could lay out your own class file, and you didn't even have to write Java code, and you could make this thing that could sneak back into the Java world and nobody would be the wiser. But this is really arcane, right? This is considered advanced voodoo Java programming because there's not an information model for programs. There's only an information model for the compiled program. Schemas are pure data. This is a definition of an attribute from Datomic, and so I'll go through quickly what's in here. This thing has an ID, which is a temporary ID because it's going to insert it into the database. It has a name, which is part/name, so it's got a namespace name. It has a type, which is DB type string. So that's the kind of things that can be stored in this attribute. It has a cardinality. Everything has only one type, so the cardinality is 1. It's full text true. It's got a documentation string. And then this last attribute is special and causes the attribute to get installed in the database. Now, most Clojure programmers, when they look at this, they immediately say, okay, I get that data representation, but every time I install a schema attribute, it's going to have a temp ID on the way in. So that feels like boilerplate. And maybe I always have to have a doc string. I certainly always have to do that install part. So why not have some sort of little function that says, make this thing, and then only the parts that vary come into play. And this is actually one of the more frequently asked questions so far on the Datomic mailing list is, wow, that schema definition has a lot of stuff in it. I want to have this little magic thing that makes that go away. And what's wrong with this approach? This has replaced something that was made out of data with what? A little program, right? A little entry point, a function that has to exist, which means that if I were going to have tools that program tools that program tools, I don't have data at the bottom anymore. And in fact, there's a really important design principle that underlies a lot of what goes into Clojure here, which is, if Datomic gives you this, can you make this for yourself? If Datomic gives you a bunch of data and says, here's what you have to say to me to make me happy, can you make data? From what languages can you make data? I'm trying to imagine the new world where languages actually make data. So all languages can make data. If the language gives you this, what do you have to do? Or if a tool gives you this, an API entry point, what do you have to do to make this thing? You have to have this thing in your hand. It has to be written in this tool. You have to have it there, and you just can imagine all the complexity that would follow on. If you lived in a world like this, then you'd have to have mocks and stubs of this thing, and an interface to describe it so you could have alternate implementations. It's just a mess. Now, I'm not saying don't do this for yourself, right? By all means, if you find something that's more expressive. But this is not the bottom. This is the bottom. So the value propositions of schema being value is that there's an API for manipulating schema. What's the API for manipulating schema if it's a map of keywords? Right? It's the whole Clojure collection API, or collection APIs anywhere. You can make them from any language. You can read them without evaluation. Right? So we can pass schemas around, read them, do stuff with them without evaluating them. It's also not positional. So one of the big advantages we got when we made it more terse was we actually encoded information in order, which means it's something else a developer has to learn. Now, that's perfectly fine when you get to a point where you're using something all the time and you're like, you know what, I really want to make, this is the thing I do all day. I want to make it easy. I'm perfectly happy to memorize the order. That's great. You should do it. But it's not the bottom. Navigation is data. This one is subtle, and my mind melted a little bit the first time I hit it. So I said before that an entity in Datomic just represents a thing, a person, an account, anything you've stored in a database. But it's not like a map in the sense of, I have a relationship to other things, but other things also have a relationship to me. And so I might want to look in both directions, which maps can't do. But databases can. This is one of the reasons why database query is so much nicer than navigating in an OO program, right? Is that you can go in both of those directions implicitly. And so one thing you could do is you could make this evil enhancement to the entity interface and say, we're going to have reverse get, so we can navigate in the other direction. What we did instead is we came up with a data syntax for navigating in reverse. And because it's done with data, you can just pass in a key that has the right shape, and that key now says, instead of drilling down, I drill up. And now, instead of adding a new interface and multiplying complexity throughout the system, you can say things like, this says get Jackstown, and the underscore is the trick for nav backwards. This says get everybody who lives in Jackstown. Right? Navigate down to Jackstown, and navigate back up to everybody else who points to that town. And that's a level of expressiveness that couldn't be reached. And remember now, we also get to stay in the game of programming with data. So if you're writing programs that write queries or writing programs that write navigation, you can use that. Which means that, and I said 0 was the right number, the number of methods in Datomic's graph API is 0. Right? The graph navigation API is underscore lets you go backwards. Now you have graph navigation. Now I want to teach you data log. I'm going to teach you data log in 6 minutes. Pay very close attention. Try to lean forward. Feel free to stand up. We're going to go fast. So here's the anatomy of a query. This is an entry point. This is similar to some of the logic stuff you've seen before, but the syntax is slightly different. Where expresses constraints. You can have one or more inputs that you're going to be processing. You want to name those inputs so that you can refer to them in your constraints. So the in clause lets you name inputs. And then the find specifies which logic variables you're going to return. Variables are named with a question mark. Constants are Clojure data. I do want to point out that this is an important place where the extensible reader works to make logic programming in Clojure a much more beautiful place, right? Because now you can build up better things out of primitive things and use them in your logic programs. We're going to look at data log against this database of 4 facts. John has the email jado@example.com, Jane has the email jane@example.com, and John has placed 2 orders, which have the famous numbers 107 and 141. For those who know a little bit about Datomic, I've cheated and left out all of the time capabilities just to make the example smaller. So here's a data pattern. A data pattern lines up with entity attribute value. So customers, attribute email, and then a variable for email. Constants constrain your query. Variables then get filled in. So for example, if I say customer is variable, I want to find email, that finds everything in the database which is email, which is those first 2 facts. If I now go and bind entity to a constant, that's going to further constrain me, so I'm only going to find that first one. Right? I'm now finding constant entity, constant attribute, variable value. I can put variables anywhere. In particular, you can put them in attribute position, which is really sexy if you're coming from a SQL background. So now it's find all of the attributes possessed by entity 42, or all the attributes and values. So now we're getting all the attributes and all their values. The where clause has those patterns in it, and then the find clause specifies which variables you're actually going to return. If you have more than one pattern, that's an implicit join. So this says find all the people who have emails and orders. And notice that you can just leave things out on the end, so I don't have to say customer, email, some variable. If I don't care about that, I just leave it off. The API for this is that function Q. That function takes that query and a database. One method in the API for query. Now, it actually has an explicit database there, and that database can be named with an in clause. So we didn't do that there, we skipped the whole in clause thing, but you can actually have an in clause that says that first argument has the name database, and then you can refer to it by name. And that looks like this. So now I have an explicit DB, which is named database. And then my pattern, notice that it's the beginning of the pattern now, before entity attribute value, has that database, explicit by name. And then now we can have a second argument. So now we can say, this is now a query that can be parameterized at runtime. Right? That second argument gets bound to a variable. Notice the question mark email. $sign database says that's a database. Question mark email says that's a variable. We're now binding that query at runtime. Of course, this is a little bit verbose, and we all know that if a name begins with $sign and is verbose, you just shorten it down to $sign. We learned that from the JavaScript guys. And in fact, you can go shorter than that. You can just leave it out, which takes me back to where we were at the beginning, right? When I first showed you queries, we weren't naming the database. Now you can enhance that a bit. You can have predicates, and these predicates are going to look like Clojure functions. Secret, they are Clojure functions, right? So this just says, and now constrain the price to be greater than 50. And so now this says find all the items that have a price, but only the ones that are more than 50. You can also call functions. When you want to call a function, the thing on the left is like a function call. Those variables have to be bound already for the function to be called. Remember that functions have an order where logic programming doesn't. Right, so we can't call the function until we've actually bound all those inputs. So we bind all those inputs, we get an output, and now we have this query. This query comes up because the manager comes to me and says, we have this problem. We have some customers, I think they're mostly out in the Midwest, and they're frustrated because they buy these cheap items from our site, and the shipping price for the item is higher than the price of the item, and that's a real emotional touch point for our customers. Like, whenever they buy something that's $5 and it costs $8 to ship, it pisses them off. So I want to know how often that happens. And it's kind of a subtle thing, right? Because you have to say, well, given the customer, navigate to their zip. So notice that those 2 lines of the query, because they both have the address variable, that gets us from customer to zip. Right? So that's an implicit join. Then we grab the facts about products that we would need to calculate how much they cost and how much it costs to ship them. Then we call out to a web service to find out what the shipping cost is. We call out to this web service in the middle of a query. It's perfectly safe for us to do that because our query is not talking to a place. Our query is against a value. So I'm not worried about, oh my God, if I tie up a thread, someone's going to drop dead. And then we constrain the price. Why did I show you this? I just did that in 6 minutes, by the way. Why did I teach you data log in 6 minutes? This is what I mean when I'm talking about evident code. Having watched this for 6 minutes, I've watched beginners who can look at queries that can do this much and piece through them and understand how the pieces fit together. If you want to really understand evident, go and write this in SQL. Go and build this and do it in SQL to see the opposite of evident. And we can talk about why it ends up not being evident. But this is a walking, talking example of what I'm talking about when I say evident code. This is only about what you're doing. There's nothing here about navigating representation, details that I don't care about. Oh, it happens to be stored in a table. Maybe that column can be nullable. What are the join keys? Right? It's all just about what I'm trying to do. Another piece of advice, if you want to have evident code be explicit, what's the worst kind of thing you can have in a program now that we don't do goto anymore? We all know that it's a global variable, right? Global variables are the worst thing that you can have. But actually, the one thing that's worse than a global variable is an ambient global variable, right? It's a global variable that's so damn global you don't even name it. It's just there. And so here we have that, right? In SQL, you have ambient database. When I showed you query before, you have an explicit database. Well, let's think about what follows from that. We've already seen that once you have an explicit database, you've gotten your juices flowing now. Oh, I could have an explicit database. I might as well be able to have more than one thing passed as an argument there, which means that we can do query parameters like this. This gets you out of the business of having a separate feature in your system called parameterized query. Right? This whole thing just goes away because you said, I'm going to be explicit about the data that I'm passing in. But of course, once you're there, you're like, well, crap. I should just be able to pass in any old data. Right? So there's system get properties. This finds me all the system properties. I'm not going to walk through all the different binding forms today. You guys can look at this table later. But the basic idea is, I could say, give me all the system properties that are path related by making a Java interop call, and then split those into their path elements. So give me all the path elements, and finally give me just the ones that are jar files. So building this out of data and being explicit has now taken us down to the point where we might as well have a logic language that you can use with anything. It started out as being about the database, but there's no database here at all now. And of course, the potential killer feature is once you're there, you can also join across databases. Right? So you can just say, notice that now I'm going to pass in two separate databases, two things whose name begin with $. And those might have originally been hosted in separate places and who knows what else. Is that your way of saying we should go down and have drinks now? Yay, yeah, I'm at slide 102. We're making pretty good progress. So the last example that I want to talk about is making tests more evident. And there's this notion that testing should be about being evident, that testing should be executable documentation. Tests have a lot of different pieces. There's input generation, there's driving the inputs through your program, capturing the outputs, validating those outputs, communicating back to you, recording so you can come back and look at past test runs. And most of the testing that we do today, complex, those of you who are playing at home, right? Complex all those things. This is a test from Clojure's own test suite, but it has all these different things put together. And I don't hate this test that much. But it doesn't show me as much as it could about the operation of the system. And it's also a nightmare to maintain. And it doesn't really tell us much about whether the system works. Like, we're really good at adding a few numbers, right? This list of numbers that we've hand-curated. So one approach you could take is generative testing. And the example that I'm going to show here is actually from the Mastermind board game. Some of you may have played this board game. I think this is I'm sure the European one is made out of wood, and it looks a lot prettier than this junky plastic American thing. This is the one I had when I was a kid. But the idea is that you're trying to guess the colored pegs, and you get scored by your opponent. And they have one color that says you've got something that's in the right place, and there's another color that says you've got a right color, but it's in the wrong place. So if you're going to test this generatively, you might start with, let's just come up with something that can generate a random sequence. So in Clojure, it's easy to choose an encoding. We'll just use keywords for the colors. And then you'll have some function. Our function is called score, and it returns. It doesn't really matter the implementation details. But the big thing is that you're going to have input generation in a separate place, and you're going to have validation in a separate place. And validation is going to try to make more categoric statements about how the system should work, instead of hand-curated, 1 + 1 is 2. If you were testing math, the equivalent would be addition is commutative, those kinds of things, and make those statements. So for example, scoring should be bounded by the number of pegs. If I'm playing a 6-peg game, the score should never have, the two components of score should never add up to more than 6 pegs. So you can make those kinds of statements as functions, and then combine them in a driver. Right, so the driver brings together the thing you want to test, the generators for the inputs, which we used Clojure's tagging for that. It seemed somewhat intuitive for a Clojure programmer to say, tags normally represent types. Now they're going to represent generating functions. So those tags are, how do I generate those inputs? And of course, you can call this function directly. One of the things I really hate about testing frameworks is when you can't do that. When the testing system runs this, it actually makes up inputs and pumps them through here, but it's just a function. You can just call it if you know how to make inputs with that shape. And if you don't know how to make inputs with that shape, those random secret's a function name, right? You can just make one with that shape. You could also just enumerate all the cases in this one. This one's so small, you can actually, rather than being generative, you could be comprehensive. So test inputs and outputs are data. And once you start thinking about it that way, then you get creative. So this is the visual testing for the game of life. Or actually, I think this was Brian's brain. Right, so it's actually, once you're thinking of things as data values, you can think of transformations. I can't really read vectors to visualize the game of life, but I can read that pretty well. Right, once I know that 0 means alive and 1 means dying, or whatever the shapes were. You could also have tests that write documentation. So this is a test from Datomic's test suite that actually tests the binding forms by printing out a table that says, here's how they work and here's what they would bind to. And of course, once you keep track of time, even stateful interactions are just pure immutable data, right? Once things are time-stamped. So you can have tests that are time series tables. This is a test of something mutable showing a series of calls. In this case, it's a series of calls in order. You'd have to have a more complex visualization if they could be out of order or interleaved. And this is a test of interleaving. So this one's interesting. This test is testing the ability of the Datomic peer to reconnect after the Datomic transactor has fallen over. So Datomic transactor gets shot in the head, problems in AWS East, whatever, and then all the peers are like, oh my God, I can't talk to anybody. And so they go into this mode of trying to reconnect, but there's all kinds of interleaving that can happen there, right? There's network communication going on and so forth. So I just devised this little language, which is really rude and obnoxious. It's got these little letters, but it's small enough that it fits on the screen as it runs, so I can sit there and watch it. And I can push it through simulated failures and see if the interleavings look reasonable. Now, of course, for extra credit, you write a program that can then process that data and says, that's an invalid interleaving. Right? That's a logic program that says that interleaving couldn't possibly happen. The other piece that I want to say here, though, as it relates to evident code, is when you're thinking about simulated failure. So this is a test that actually, it prints a dot every time it successfully writes to the database log, but it keeps track of internal failures. So there's this 9 retries. And a lot of times when people are testing this kind of code, what they end up doing is manufacturing this new ecosystem that's just around testing, mocking and stubbing and what have you. And the fact of the matter is that that retry is an event in my system that matters enough that it must be producing a side effect that I can see. So it's much better and more evident to actually test your system than to make up this whole parallel ecosystem that isn't your system. Right? If this thing is not important enough to have any side effects, I would argue that you do not have to test it. If it really could not possibly affect the operation of your system, you don't have to test it. If it can affect the operation of your system, then it does have side effects. And you may have to do some things, right? You may have to speed up time. You may have to do things, noodle with making failures happen quicker or something. But you can get this information out of timing, right? I hit something and I was forced to retry because there was a problem, so that would run slower, so you'd see these blips in the timing. You could get it out of the logs. In this particular case, I'm getting it out of the logs, so I just wrote this nasty log string parsing. All the log as map people in the Clojure community should beat me up. But the logs are what they are, so pulling that stuff out. But you could do a better job there as well. And my point here about testing is try to stick with your programs. Work on your programs, not on your tools. And now I am going to skip a couple of slides. I'm just going to say there's this really awesome thing called the sim that I refuse to tell you about. You're not allowed to know. But if you come and talk to me over drinks, I'll talk to you about it. And I want to sum up by saying the building blocks that I've presented today are nothing new to anybody. Right? The only things I've presented here are be declarative, try to be functional, try to be logical, use abstractions carefully, and program with data. Simple advice, surprisingly hard to live up to rigorously. Right? It's not in these top-level bullet points that the magic happens. It's in the details of doing these things. And the Clojure jar itself, some of the library code there is a great place to look. And also a really wonderful example I should mention, particularly about evident code, is look at the difference between Clojure script and Clojure. Go read the bottom of Clojure in Java and see how evident it is what's being built. And then go read the bottom of Clojure script in Clojure, right? It's, reading the Clojure code base is an exercise in re-having the pain that Rich had 3 or 4 years ago. It's not really about learning to be a good programmer. It's about learning the pain that you have to go through to create the baseline level of abstraction. But reading that even at the very beginning, the very top of core.cljs or whatever it's called, is beautiful from day one because you have the tools in hand to write code that's evident. So, let's go downstairs and have drinks. Thank you.